will let you kind of interpret things and understand a little better when you're looking at information for individual fixtures and whatnot. So this is the meat, right? This is lighting. We're going to talk. Somebody even brought it up after my last session of how you relate things to each other between candela and lumens and all that sort of thing. And that's what we get to do tonight. All right. You all know the disclaimers. There we go. We're not going to read those. Oh, okay. And then when we had our very intro, when I was down there in person and I talked to people about having to, in my first lighting class, have a cheat sheet, right? That's these 6 metrics that they're talking about. I had to have that stuff down on my lap to understand the relationship between all of them so that when we talked about other things, I could pull it all together. So don't be afraid to have cheat sheets, right? Here we go. All wonderful things. Again, I am not good. One thing I truly try not to do is read slides. You guys have eyeballs and brains. You can read stuff on there. If there's something noteworthy, I will come back to it, but I'm not going to read slides to you. That's terrible. All right. So again, photo and metry, right? Light and metrics. So photometrics. What light then is a measurement of radiant power across the spectrum, right? But what we call light and what we call lumens and all that stuff has to do with how our eyeballs react to those various and sundry wavelengths, right? So one of the things they didn't do in this section that I think they really should have done a little bit more, and I will tell you about right now, is show you what's called the V lambda curve, and that's the human eye response and how we respond across the spectrum, right? From red all the way up into blue, and how our eye sees an equal unit of energy at each of those. We're more sensitive to the middle, right? 555 nanometers where we're peak sensitive to. And as you go to the sides of that, we're less and less sensitive, right? So an equal amount of energy at a high blue, we don't see as much of it because we're not as sensitive to it. And that V lambda curve applied to whatever it is that's coming across lets you know how humans see and how much light there is. So light is different than radiant energy, right? Light has the human thing put into it. And people discovered and went through lots of experimentation long before computers and things to figure out how our eyeballs responded. Now, one of the little notes then, as a subtlety to that, is that human eye response is done at daytime light levels. So when you want to get into nighttime stuff, there's a little shift. We're not going to do all of that. That's much more deep, right? But know that the V lambda curve converts radiant energy coming in across the visible spectrum into what we then see as light, right? And this is the cheat sheet right here, okay? Lumens and candle power and illuminance and reflectance and excitance and luminance, all right? So I did read it, sorry. We talked about this last time, and we talked about, when I talked about light sources, about lumens, right? That's the most common thing we talk about. How many lumens does that light source have? What's really fun now is that the light sources and fixtures that we talk about, you talk about their lumens, and that's actually how many are coming out. We used to have to talk about the lumens in the lamp, and then we talked about the fixture efficiencies and then how many lumens might leave the fixture. And then we had to figure out how many lumens were actually coming out of that lamp, because it's really not the lumens that were in the catalog, because you put it on a ballast, right? You guys are entering a whole new wonderful world where you look at a spec sheet for a fixture, it tells you how many lumens are coming out. So lumens per square foot then, right, is illuminance. If you take a lumen, drop it onto a square foot, you have a foot candle. If you take a lumen and drop it onto a square meter, you have a lux. And that's where this ratio between lux and lumens is really the ratio between a square foot and a square meter, 10.76 to 1. A lot of people will, if they're dealing with metric, they'll just kind of shorten that to 10 to 1. So if it calls for 50 lux, you know it's 5 foot candles. Real number is 10.76 because that's the ratio of the two areas. And actually at this point, I want to stop sharing or not. I will show you a thing later, not too much later, that lets you see that relationship. I found it in a book and I can wave it in front of the camera for you guys. Candle power, right? This is another thing we got into last time that really is not fully investigated here. What a candela is a lumen per steradian. And what a steradian is it's a cone of light coming out from a center point, and a sphere of these things is defined as 4 pi steradians. So an entire sphere contains 4 pi of these cones, so 12 of them. If you put a lumen into each of those cones, you have what's called a candela, and the lumen goes into that cone forever, right? And the cone just keeps getting bigger and bigger and bigger and bigger and bigger. And there's just one lumen all the way out there. So when you slice the cone, you have a certain amount of area and you have one lumen onto it with one candela. If you get out to where you have 1 square foot, which is a foot away on a sphere, and I'll show you that thing later, right? 1 square foot, 1 lumen, 1 candela, 1 foot candle. There's the relationship. There's where you get to a lumen per square foot going into that cone, right, of 1 steradian out of 12. So a source of light that has a luminous intensity of 1 candela in all directions produces 4 pi lumens, 12. Right? And sometimes it can be kind of handy to understand how those things go back and forth together. Reflectance information, if you bounce something on, how many come off? And there are different kinds of reflectance. There are diffuse reflectance and there are specular reflectance. And then actually a lot of real life happens somewhere in between, right? If you do painting things, difference between matte, semi-gloss, and gloss. If you think about how light bounces off of those 3 things, right? Matte is diffuse. Gloss is getting much more like a mirror, although there are still some bits that come back to your head, back to your eyeballs when you're looking at something, unlike a true mirror would be. So, real life materials are often a blend. Calculational engines typically only count diffuse bounces. So how close are those things then to reality when you have, I don't know, places with interesting textures on walls and things like that, as opposed to just paint? So things to keep in mind on reflectance, specular, and diffuse, right? And then excitance is how much is coming off per square whatever. Now, what they describe here in terms of luminous excitance with M is valid pretty much only for diffuse surfaces, right? When you get down to true luminance, which is the next one down, candela per foot squared or candela per meter squared, that then describes the light coming off of a surface in directionality, whereas the luminous excitance is assuming a diffuse reflector. So diffuse reflectors, when you bounce light onto it, no matter which direction you look back at that diffuse reflector, it's going to look the same because of the way that the diffuse thing reflects light, right? And as you work your way down, there are cosine angles, which we'll get into big cosine soon, right? Where looking straight down, you get the most. That's great. Looking at 45 degrees, you get only 0.707. We'll talk about that in a second in terms of how much light's coming off. But then there's also that much less angle to be looking at. And so they all balance out. And so the luminance of a diffuse surface, no matter which way you look at that dot or that amount of light on a tissue paper, it looks the same to you. If you turn that tissue paper into a mirror, it's nowhere near the same anymore. And if it's a laser coming in and you get right opposite, you'll burn your eyeballs. Right? So luminance describes actual light coming off in directions. Excitance is really only valid for diffuse surfaces. And I hit the wrong keyboard, so I got 2 here. Close that out. We're not going to go too far into this little chart, but it does talk about real life things that you will encounter, like light meters. Which, where'd it go? I have a light meter around here somewhere to show you guys. I don't know exactly what I did with it now. We'll see. And that was an illuminance meter when I say light meter. There are other meters that can measure how bright a thing is you're looking at, like the light in my face right here. And there's an acceptance angle circle in that luminance meter where you can actually measure luminance coming off. You hit the trigger and it tells you. So that's something you might encounter. They're kind of expensive. Illuminance meters can run anywhere from, I don't know, cheap to expensive. Luminance meters don't even start cheap. There's no such thing. And then there's also, I've seen folks be interested, who are very interested in color, get a radiometer where they can actually hold this thing up to the light source or the light bouncing off of something, and it will tell them the color composition of that thing. If you're getting into color a lot, that becomes very important to you, and so do things like TM30 that we'll talk about later. The rest of it, again, we're not going to get too much in. All right, this is very important. In fact, this is so important. They should have emphasized it more because it has a lot to do with how accurate our calculations are later. The way that we measure light coming out of a fixture or a lamp or a reflectorized something or other, right, is we put it into the lab, and 25 feet away via a bounce typically, right, we measure how much light that thing is throwing at that particular angle, and then we rotate it, we measure again, we rotate it, we measure again, we rotate it, we measure again, right? And you do that for a full investigation of either a hemisphere of data or a full sphere of data individually, and you record those values. They translate those values back into a candela table, and we have this wonderful table of how that source puts out light when it's really far away, right? When it's acting like a point source. So I have people ask me all the time to do calculations of things like a cove, where they want to take the light source and bounce it into the cove and get it out of there. Well, your, say, 1 foot piece of cove material gets a test done at 25 feet away. And then what you're asking the program to do is take that information that's based on 25 feet away and interpret it 2 inches from the light source accurately and somehow get the light out of that cove. And that just doesn't happen. Right? So keep in mind when trying to do calculations, especially with calculation engines and lighting analysis programs, that you might be able to build the model really nice and aim a fixture the way you want to. But our whole basis of photometry is on that light source being like a point source. So even worse would be to use a 4 foot long test inside that cove. Better be a 1 foot test, better be a 6-inch test. You could take that 4 foot test, multiply its output by 0.25, modify it into a 1 foot fixture, put 4 of them in there versus 1, and go look at calculations and see how different that comes out. Right? So keep in mind, all of our photometry is based on far field photometry. So the light fixture up in the ceiling versus the work surface still isn't even 25 feet, but at least it's 6, 7, right? But then coves are very difficult, and I really try not to count too much on the results of things far field when you're really looking at near field. Right? More than you probably ever wanted to know. All right, here we go. Interior photometry. This on your left-hand side is well, it's several slices. The white and the thing with the arrow going out to the end of it at 1100 candela at 112 degrees is a slice through the fixture, right? And then you look at the side view of that fixture and how that fixture is putting out light. So if we're looking at, so what that white section is you're looking at the end view of this light fixture that hangs down into a room. It's got a fair amount of light coming down. You can see it's the area under the curve, basically, is the light in this cross section. And you can see it has a very high peak candle power going out across the ceiling. So this could be a very uniform ceiling. And then even down below, notice they do a double bubble sort of a thing where you don't just have a spike below or a circle. They've actually tried to push that peak candle power out a ways for more uniform illuminance down below. And we'll talk about all that wonderful change in illuminance due to distance and angle, that they're doing a good job in this particular fixture where we're coming down there, right? So that's one slice. And what they do is they test straight down, and then every few degrees going sideways all the way up, and that's what this view is. And then it's symmetrical both sides. So then the next line in is, instead of looking at the end view of this fixture, anything like a fixture here, let's call this a fixture, right? So it's kind of long, right? This is your fixture. So we took a slice this way, and that's what we were looking at with the big spike. Well, now we turn the fixture 45 degrees and take a slice through. And notice that the candle power is much less than the crossways. They're really trying to throw it crossways. And as we now go 45 degrees in, it's ramping back in. And then we get down to the dashed line, and the dashed line is, instead of cutting the fixture this way, we're cutting it this way. And notice that on the dash line, it doesn't have this huge kick at the end of this fixture anymore. It's just kind of what's left over. Whereas when we go this way with the fixture, you have this huge kick running across the ceiling. So this would be a linear fixture running this way in your space. Right? You put one here, and then you put one over here somewhere. And between them, they light up the ceiling and then take care of below. So that's how you kind of have to think about these diagrams. They're slices that look at how light comes out. And then there's tabulated values of those are your candela tables, right? This is a table turned into a graph. Anybody have any questions about that? Because it's super important.
Negative. I do not.
Very cool.
I think I'm good.
Okay, good. Good. All right, here we go. All right, now this one, don't trust it. It actually has a large error in it, right? Oh, what this is a outdoor fixture that had a the blue line that we're looking at is that slice, right? So that slice is through, if you're looking in plan view at a fixture in 360 degrees, and you find out where the maximum peak candle power of any of the values is, whether it's at 0, 45, or 60, looking down on it, you take a slice through that. And that's what the blue is, right? And that shows you that the peak candle power in this particular fixture happens at about 82 degrees above ground, right? That's what that blue spike does. 90 is straight across. I'm coming down 10, maybe 18 degrees. And it has a certain value there, right? And so that shows you got a pretty good punch down out of this fixture, ramps back up, and then kicks way out there to try to give you some uniform, probably a type 4 outdoor lighting fixture, right? Now, what the red is, pay no attention to the text on the screen. The red shows you, how do I describe this one? Where that peak is, that 18 degrees now down below. If you were to take your arm, go straight out, come down 18 degrees where that peak is, and then sweep your arm around yourself as a pole, that's what the red is showing you, right? So it shows you that this particular fixture is kicking a lot of light up the street, a lot of light down the street, and not so much forward. So this is a very skinny, long distribution. So you're looking at what's called the cone of maximum candle power, right? That cone of 18 degrees down is what that is. Pay no attention to the red text, right? You won't typically get too involved with that. I do a lot of outdoor lighting. Most of you won't, but it's good to know what that really means. All right, here we go about photometry. So photo, remember, light, and metry, measurements. A lot of times we're interested in the output of a something. A couple different ways to do that. You can do the full investigation like we talked about, all in the goniophotometer of all the values and all the way around, up and down. You take those candle power values, you go into zones. There's a zonal constant you apply to the zone, you get lumens in that zone. Add up all the lumens, and you have all the lumens, right? Well, that is a very much more intensive time and effort to get that kind of an answer. If all you want to know is how much light comes out, you can do it in an integrating sphere. And what that is a thing that hides the view of the sensing source from the source of light, right? Sensing source, the sensing receiver, I guess would be a better way to call that, right? So you have a source, you have a thing that hides the source from the receiver. The receiver is getting light then bounced. And in an integrating sphere, when you turn it on, it takes almost instantaneously, comes to equilibrium with all the light bouncing around the place, right? So your sensor gets a reading. Well, you had a source of known lumens. Now that has to go to a lab occasionally and be verified that that source is the proper lumen source. You know what the reading on that sensor was for the known lumen source. You got a new reading on the new source of whatever it is, whether it's a lamp or a fixture or a, whatever it might, or a candle, I don't care, right? And then you ratio the two and voila, you have the lumens from a single measurement. So if all you're after is lumens, integrating spheres are an amazing way to get some information as to how things are working. Oh, wrong keyboard. Go away. There we go. All right. So then comes the photometric report. So when I talked originally about taking this into a goniophotometer, mounting it, doing the investigation of 360 degrees, and then 0 to 90 or 0 to 180, and tabulating all that is candle power and luminance information. But then some photometric reports can also do color information, and that's what you see some of over here on the far right-hand side. Shows you the color of the source in a couple of different ways, right? Again, for people who are super interested in color, these are important. Lots of you guys won't have to dig that deep, but it's there for you should you choose to. Okay, understand that well, it can be there for you if they tested for it, right? If they did the radiometric testing to find out how this stuff was going. Lots of times in a quote all the time in a quote photometric report, according to IES LM63, that's just lumens. Color is a whole nother thing, and we'll talk about that later as well. All right, so here are those tables I talked about that got turned into a graph. So on the left-hand side, you will see a graph of a very diffuse sort of a fixture, call it a 2x2 lens troffer or something like that. And then a zonal lumen summary down below that tells you how all the lumens are spread out. The candle power tabulation is the next page. Look at all those wonderful numbers. I like numbers. And then actually down at the bottom of that second page, I don't know if I can actually zoom in there or not. But it talks about average luminance at different angles. And it starts at zero, at straight down, looking up at the fixture, one piece of data. And then it goes to 45 and starts investigating above 45. And what that's for is to tell you how bright that thing is from afar in the room. And documents like the recommended practice for office lighting will have some limitations on how bright a fixture should be at those angles. And this is where you can find that information off of a cut sheet without having to do your own calculations. Some lead things and some other kinds of, I'm going to get points for being good things, right? Will have some of the same kind of limitation information. And this is where you can go to find out if the fixture you're choosing is going to meet those limitations. Right? Coefficient utilization chart is next, and we will go much more deeply into that in a while. And then they talk about beam and field angles. Well, we'll talk about that a little more when it comes up on one of these charts. All right, so we're back to this, talking about vertical angles. There's our chart of candle power values, right? From 0 being straight down all the way up to 90 being to the side. Notice this particular fixture has an opaque side. So when you get up to 90, it's got zeros, and then it starts up again. And notice it goes through the peak and then starts dropping down again. So all those numbers are candle power. Anybody remember what a candle power was? I heard somebody say something that was really faint though.
Don't remember, sorry.
The lumen per steradian, right? It's a lumen per one of those cones coming off of our sphere. So these numbers are independent of distance. They just go forever at that number because it's that many lumens into that cone. How far away in the cone you are then varies what your quote foot candles will be, because the cone gets bigger, but the lumens stay the same. 189 lumens at 55 degrees vertical and 67 degrees horizontal, going forever. So you combine that information along with distance information and incident angle information. We'll see the formula here shortly, right? And you can figure out foot candles from candle power, but candle power are independent of distance. You can only figure out foot candles once you know how far away you are and at what angle you're at. So doing calcs by hand, you have a lot of interpolation to do on something like this, right? In fact, for an indirect direct fixture, it's almost impossible because you have to bounce light. But let's say we only had the direct values of this fixture. It was that little bottom thing only, right? And you were, 8.5 feet away from a fixture where your desk was. Well, you'd have to figure out relative to this fixture, how many feet over, how many feet down, use trig to figure out some angle values, come back into this chart, find out what the candle power is at 57 degrees relative to 55 and 65. And maybe it's not even at one of these other angles. So you might have to interpolate between 4 values on the chart to get the proper candle power value to then plug into the formula to figure out your foot candle. Now, we got computers that do all that cool stuff for us now, right? Be a lot of hand calculations. All right, here we go. Here's average luminance in big. I don't have to pump it up for you, right? So candela per meter squared. Notice we mix up a lot in lighting, metric and English values. That's one of the reasons I started with lux and foot candles, because a lot of times we don't talk about candela per foot squared. We talk about candela per meter squared. Right? And intensity is just candela, no anything yet. How many of those candelas, though, do we have coming off of a surface that's a meter squared? And that's how you count back and forth between those. All right, here we go. Ooh, adjustment factors. Actually, I thought this one was pretty interesting. So here is like a downlight. Notice that the candle power chart is number 2 here is much more simple because in a downlight, it's completely symmetric. So no matter which angle you look down on it, it's the same number, right? You come out to 45 degrees, it's 175 candela, no matter where you go around that entire fixture, okay? And then what they did over here, interestingly enough, is they lumped lumens by angles somehow, so you could kind of see how the lumens were concentrated. Didn't do a very good job of telling you exactly what they were doing, but it shows it pretty well. Center beam candle power, if you were to be right below this fixture, initial center beam foot. Oh yeah, okay. If you were to be right below the fixture at these distances below, that's how many foot candles you'd have. That's the very simple calc that we'll come to later. I want y'all to pay attention over on the right hand side. Part of mine is obscured by myself, but when you go through in LED land, which is what you'll be dealing with, when you go through different color temperatures and different color rendering indices, I think I said that right. You will find that output changes. You push to higher CRI, your output drops. You push to warmer colors, your output drops. That all comes back to me showing you that blue LED that gets phosphor converted, right? The farther away we get from blue, and the more red we try to keep, and that's where the 90 CRI comes in, right? The less and less light output you get. So this particular fixture, if you look at that very bottom one on 90 CRI 2700K, it says 70-something% of what the initial output was. So just blithely writing down catalog numbers can really affect your output. You may think 90 CRI is always better. Well, it's always better looking. But are you willing to give up 20% output and consume 20% more energy for the same foot candle level in there to get to that 90 CRI? That could be very important for places that sell produce. Any other kind of agricultural product that you want to see the colors on, right? Fabrics, things like that. It's super important to maybe get high CRI. But if you're lighting an office and people are working on computers and looking at black and white paper, 90 is not required in the slightest, right? And you don't have to pay that performance penalty. So that was just a nice note on that particular sheet. Spacing criterion, you'll see this on lots of individual fixture performance information sheets. It refers to how far apart in terms of mounting heights you can place fixtures, and at that distance below by one mounting height, get an even line of calculational points. No bouncing or anything going on. So if you have 1.1, right, and your mounting height was 8 feet, it's 8.8 feet on center. They really shouldn't do tildes, right? It's 8.8 feet. You would space that particular fixture to get even foot candles down below. Now, a lot of times we can allow for less than even. Right? You don't need perfect uniformity in a hallway. So you can probably go beyond that, but then you have to, somewhere in that whole thing, count your lumens and see if you're going to have enough light overall to space out farther than what that means. And even at the spacing number, well, how many foot candles do you have? If it's a 10-watt source versus a 100-watt source, they can have the same spacing criteria. One will have 10 times the foot candles as the other, but they'll both be perfectly even. Spacing criteria. All right, here we go. Field and beam angle. Field and beam angle are typically reserved for descriptions of things like floodlights, spotlights, reflector lamps. Not typically reserved for things like 2x2 panels or really even downlights, which is what they kind of have pictured here. People don't tend to utilize those terminologies for things indoors, basically, right? Outdoors, we talk about field and beam angle, has a lot to do with floodlighting. When you get the floodlighting, utilizing the beam angle, the 50% numbers where you get the most of your punch, right? And then what the field angle talks about is who's going to see what from how far away. If your field angle is very tight to your beam angle, that's very good. That means you go from all the light that you need to nothing very quickly. In the days of metal halide lamps and HPS lamps and floodlights, you could have a nice reflector behind your lamp and get a good tight beam right out that way. But then if you saw into the fixture from all the way over here, there's still that bare lamp number. So you can have a field angle, 10% of your maximum candle power, that's way fat versus your beam angle that could be way skinny. Right. And that's not such a good situation. But if you saw that there was that much of a differential between the two, then maybe you might not choose to use that particular fixture if spill light and glare from afar is concerned. So field angle is 10% of the maximum candle power out of that, whatever it is. Beam angle is 50. 50 is the usable number. 10 is kind of your nuisance number. How do those two interact? Again, typically reserved for floodlights, spotlights, outdoor style fixtures, as opposed to, and not area lights, but outdoor style fixtures that have a beam meant to project, right? Versus most indoor styles. All right, I have no idea what time it is. I know. Okay, good. Here we go. All right, let's see. All right, this gets us into a little ahead of time into rendering. And rendering is a difficult thing because all of these programs, again, we talk about diffuse surfaces, and surfaces are not necessarily diffuse. And texture, how do you get a computer program to give you back texture? So take all renderings with a grain of salt, right? Try to, if at all possible, do things like mock-ups to establish how things are actually going to look, because renderings can be very misleading. All right. Oh, here's color, right? So if you're really into color, I wish they would have chosen a color source that was a little more wonky, right? Because that center, that number 3 is really the key here. In looking at the entirety of the gamut of colors, the black circle is perfect for this particular thing, right? And the red line is the thing that we tested. And notice that red line doesn't vary much at all from the black line. There's a little bit on the outside down in the blue 12 number, right? There's a little bit on the inside of the yellows 4 and 5, but you almost can't tell. I wish we would have found one that was just terrible in some color. And we would have said, you know, if it was terrible in purple, it goes all the way to the inside. It doesn't come anywhere near close to, say, color fidelity, your number 6. Take a gander over there. If we had super low number on one of those, we would say, don't light your Rockies merchandise with this source. Because if it's going to be really weak in purple and you got a lot of purple to light, you don't want to use it, right? So these are the information, or this is the information you can pull from a report like this if color fidelity is very important to you in whatever it is you're trying to light, okay? So lots of really deep information. I don't even know a lot about a lot of this because I don't deal with a lot of color. But that's the point of TM30, is a way to do a much, 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 much more specific way of talking about color than color rendering index. Color rendering index we use a lot, and it has a value, but it's also an average. And the average doesn't tell you squat about the individual colors up and down the spectrum and how that's affected, right? So they've got these R values, and who's represented here somewhere? I don't think so. Oh, there's a more wonky one off to the left. Right. See how that one on the left-hand side under number 1 instead of number 3 has a much bigger change from the median one? Probably wouldn't want to light things where color is important with a source like that because you're deviating from what's supposed to be good. Right, so we'll leave it at that. Again, you guys aren't going to have to delve in too much, but know it's out there if it becomes important. All right, here comes the meat, right? A lot of our lighting decisions are based on quantity. And we talk about the whole foot candle thing. I'll bring it right back up. Foot candles, lumen per square foot. There's numbers that people say you should have for X, you know, whatever it is you're doing. There are values for cameras that you're supposed to have for security. There are values for roadways and values for offices and values for schools and gyms. And, you know, all of those get covered under a lot of the IES recommended practices, to where folks have gotten together either in committee or over time and kind of figured out what good values are, and they publish those. So how do you get to those? A couple different ways. And the most biggest one that we use nowadays, is, of course, is point-by-point computer programs. But we're going to show you what goes on behind the scenes of beyond computer program. Okay. Right. So point method. Point method is where the candela and the distance and the incident angle come into play, right? So we were talking about a lumen per steradian, and we're talking about how many of those per square meter coming off as luminance, all this other thing. But we've got our fixture table of candela, and then we have our geometry of wherever it is the fixture is versus where we're trying to analyze. And once you work that stuff out, you can use a pretty simple formula then to figure out how many foot candles you get relative to where your fixture is according to the photometry for the fixture. Right? And there she is, right? E equals I cos theta over D squared. We haven't gotten that up here yet because I'm going to get into trigonometry next. In fact, I might just do it right now. So illuminance E, don't ask me, right? That's foot candles. Why it's not F. It just is. It always was and always will be. So that's lumens per square foot equals the intensity coming in the direction from the fixture to your point. Now, that's intensity, whether it's no matter what the fixture is, no matter how it's aimed, there's going to be a candle power value that you have to figure out what is coming towards your source. And then this cosine theta, this is really important. I did a whole thing on cosine theta here that we'll next get into. Because if you're straight onto a source, cosine of theta is 1, and you get all the light. If you, so let's say, I need this on paper. That's how it works. So if I have this, and the light is coming directly at it, straight on, it captures all of the light. If I turn that infinitesimally thin thing this way, it captures 0 of the light. And the way that it captures it, it's relative to the area that you see, right? And the area that you see as you do this is governed by the cosine of the angle at which I tip it. We're going to get into that. In fact, maybe now it's time for this. I'm going to stop sharing so you guys can see something big here. Hopefully I can start again. All right. Do you guys see me large now?
Yes.
Cool.
Yes.
All right. So behind me. All right, children, we are now back to basic trigonometry. This is very important stuff here because this cosine angle rules everything in lighting. So we're gonna backtrack just a teensy bit into SOHCAHTOA, right? Sine of an angle equals the opposite of that angle divided by the hypotenuse, right? So the sine of 45 degrees is 1 over 1. Sine is 1, right? Cosine adjacent over hypotenuse. The cosine of 60 degrees is 1 divided by 2 or 0.5. Or TOA, tangent, opposite over adjacent. The tangent of 30 is 1 divided by radical 3, whatever the hell that turns out to be. Okay. These are all very useful when you try to figure out, when you're doing a direct calculation, what your angles are, right? Another super important piece here is if you have 2 parallel lines and you have a line coming through those, opposite angles are equal, right? And this angle plus this angle equals 90 degrees. So if you remember all of that as you roll into things, when you get into that E equals I cos theta divided by the distance squared, because you have to figure out distance, and these all come into handy for that, right? Becomes very important. So easy values to remember, though, are, 45s are 1, 1, radical 2, and 60, 30, 90, of course, they're all based on 90-degree triangles, right? Have these 30 degrees opposite, 2 opposite the longest, and then radical 3, 1.7 something opposite there. And so you can do sines and cosines just by looking at those things and knowing what they're. Now, magic, here we go. Ta-da. All right, can everybody see that one too?
Yes.
Cool. So there she is, E equals I cos theta over D squared. There's your light source. There's your distance. This is called the incident angle. Now, they don't pay enough attention to that terminology in these slides, right? You always want to be able to figure out the incident angle, because if this is straight above, the incident angle is 0 and the cosine of 0 is 1. Here's the cosine function. So here's 0 degrees. The value is 1. If we move that fixture to where that incident angle is 45 degrees, come over here to 45 degrees, run up. If you come across 45 degrees, your cosine number is now 0.707. So you've lost 21 point, well, whatever 100 minus 707 is, right? Almost 30%. So in the first 45 degrees, you've lost about 30%. Well, that means that the next 45 degrees, you lose the rest. So it really starts to matter when you start to get down here what cosine is, when you get down into these lower values, right? So if we get to, let's see here, at 75 degrees, the cosine is 0.25. You've lost 3/4 of your light by tipping that thing I used, right? 3/4 of your light by tipping that thing 75 degrees. Because you're letting all the rest go by, right? Essentially, if you think about it in terms of like this, right? You get to, what I have here, 85 degrees, you're at 0.08. So all the same candle powers, you just take that thing that you're lighting and you start to tip it from straight away to it's getting almost parallel to that thing, right? 85 degrees, you're only getting 0.08 of the relative value as opposed to straight on. So that becomes another thing that messes with rendering programs and whatnot, is trying to take into account the value of things like texture on a wall and what's going to come back to your light. It doesn't know anything about that. So when it gets down to 0.08 really quickly, as you go down a wall from a very close value, right? The renderings stop looking like what they're supposed to. Okay. So I have an example over here to the right then of a 10-foot ceiling. I know the numbers are too small for you to read, right? And I'm 18 inches back with a wall wash fixture, okay? So as I go down that wall to calculate points, no matter how the intensity is changing out of the fixture, we get these lowering cosine values to plug into the equation, right? So at 18 inches down, we're 45 degrees away. So the cosine value for the calculation there is going to be 0.707. As we roll down our wall, if we get 5 feet down from that 18-inch setback, I'm at 73 degrees incident angle. Now remember, this angle is this one now. They try to confuse you later in this about switching to sine instead of cosine. Think about incident angles, right? So the incident angle here is 45. The incident angle here is 73. If I come down to 2 feet off the ground, the incident angle is about 80, right? You have 80 degrees coming through here. So at 80 degrees and a 1.5 feet back, our cosine's already down to 0.18. Well, now if we try to do a grazing calc, okay, so instead of 18 inches back, only 6 inches back, that same 8 feet away, instead of 0.18, and now I'm at 0.06, 8 feet away, 6 inches off a wall. So the calculations of foot candles as you run down that wall show you that there's nothing there. You're like, what? There's only 0.08? Well, things that you do with wall wash is you really try to intensify the candle powers at the very bottom angle to overcome that 0.08. And then as you rise the wall, you pull back on the candle power. So if any of you look at the side view of wall washers, you're going to find a big peak to try to overcome the 0.08s of the world. And then as you come back up the wall, you will find them ramping back that candle power so that when you get very close, it doesn't overwhelm up here relative to down below. In fact, you're trying your best to overcome not only the cosine, we haven't even talked about d squared, right? The distance squared is also huge. So as you go down that wall, 8 feet away from, say, 5 inches off, that's about 64 for d squared, as opposed to 2 feet down, which is 4 for d squared. So divide by 64 instead of 4. Add that cosine thing, and you can see how calculations for wall grazing don't show what's going on because of these things. So again, keep in mind numbers you see, and keep in mind that visual things developed may or may not reflect reality. Because in a lot of cases, if you come down that wall and you have some good texture, that texture will catch the light at a much better angle. Right? So if you take that same calculation grid that runs down this wall, and instead of having the meter face out from the wall to get the measurement, turn the meter this way so you can see how many foot candles, if you were to take the meter up and down like this, you're going to find there's a crap ton of light in places where it's almost straight on, but almost straight sideways when you go back to doing the vertical foot candle calculation. Right? So this cosine and this distance squared interact very quickly. And this is why you see lots of distributions for performance fixtures have spiky distributions, and they want to throw that spike at the far out places to overcome distance squared and overcome the cosine angle. These are super important. All right. I think that's it for that one now. I'm going to go back to sharing screen. See if I can do that. Wait, nope, that one. All right. Can you all see the EID squared cosine again?
Yes.
Fantastic.
I have a quick question about this, if that's okay. So is this measuring like luminous intensity flux, basically?
Aha. So you've mixed up a couple of terms there, right? So flux is what we call the lumen, right? And in reality, what flux is the radiant unit of energy per time, but we call it a lumen. And you think about it as drops. Intensity is how many of those drops per solid angle you have. And then illuminance is how many of those drops per square unit area you have.
Okay.
Right. So it's how, what are you doing with that lumen? And then where does that word happen? Right. Lumens per solid angle or intensity, right? Because they go forever. Lumens per unit area are illuminance. And that's what we're all trying to find out in a lot of cases. Then, right, remember the cheat sheet, lumens bouncing off of that surface in a direction are now called luminance. And luminance will be the same for anything that's diffuse, no matter how you look at it. But when you get into real life, things like mirrors, totally different. And that's why I say roadway calculations are very difficult without a program, because you have to take into account where the light fixtures are, what type of road surface it is, and where the observer is exactly, because that road surface reflects light differently depending on the incident angle of the light. Regular like tar pavement with rocks in it is actually pretty shiny, I guess, if you want to think about it that way, at high angles, but not so much straight up. And every little difference there would have to be accounted for, incident versus going off of. All the programs we use talk about the surfaces being diffuse, so they don't have to worry about how differently that reflective material bounces light relative to the incident angle of the light. It just bounces it perfectly because it's diffuse. Did I answer it?
Yeah. Thank you.
All right, good. Okay, I did a lot and might be able to skip a bunch of things. Now, where am I at time? I want to make sure I leave my friends some time. 6:20, 10 minutes for an hour. Okay, here we go. I might not make you man calculators now. We'll see. Why are you not working? There we go. See, we went over all this already. I just showed you everything this thing talks about in I think, a much better fashion so that you understand these things, right? We're not going to do that much. Oh, angle of attack. All right, this one pisses me off. Sorry, bad language. Incident angle, right? Figure out the incident angle, and then the cosine thing works no matter which way you're doing, whether you're doing it on the floor or you're doing it on the wall. The incident angle is from the perpendicular to the surface to the incoming ray. If you think about it that way, you never have to mess your head up with sine, cosine, vertical, just figure it out, because you also know things about opposite interior angles, and you know that those two angles add up to 90, all those things. You can work out what the incident angle is for any of the calculations that you have to do. Angle of attack. Incident angle is the word. There we go. Here we go. So that's the way I've just talked about as what it should be on the left-hand side here, right? There's your wall, there's your perpendicular, there's your incident angle, right? Cosine, I guess they call it A there, or whatever it is. They didn't give you, they should have put the dash in at the top as well so that you could see the opposite interior angles being parallel. That's what I showed on the wall behind me earlier, right? So you can translate angles from one side of this thing to the other. knowing the two add up to 90 on each side, and knowing that parallel lines with a line going through them, the opposite angles are equal. Okay. On the right-hand side, they do math jujitsu so that you can do sine instead of cosine. It's, I don't know. It bothers my head. It might do very well for you to think about it that way. But again, I try to focus just without doing math jujitsu on the incident angles and the cosine. Right? Here's the d squared part. So E equals I cosine theta divided by d squared. If you look at that third number 3 there, right, straight down, the cosine of 0 is 1. So the cosine goes away. They didn't quite tell you that there. And that's why if you want to know the illuminance straight below a fixture, you don't have to fart around any cosines. You just take the candela value of the straight down of that file, whatever that fixture is. Now they show a par lamp here, it could be a 2x2, whatever it is, right? Straight down divided by the distance squared, you have foot candles. Easy peasy lemon squeezy, right? Back up to number 2, call it a 2x2 again instead of a par lamp or whatever it is they got pictured there. If you go so many degrees away, now you've got okay. So remember parallel lines and opposite angles. Whatever that angle is that you're seeing there that they defined as phi there coming from straight down out to the thing is also your incident angle. If you go to the other side, go down below, draw a line up, opposite interior angles, they're the same. So that phi will be valid for there and then also your incident angle. Okay. And then you'd have the cosine of that and you'd have to figure out what D is. That's where all the triangles that I had up earlier. On a 90-degree triangle, a squared plus b squared equals c squared. Sorry about the a, b, c, and d here. But the up-down value, the left-right value, if you square those two, add them together, do the square root, you can get d. But you really don't need to because you're after d squared. So you don't even have to do the square root, right? If you know the left-right distance on the bottom and the up-down distance there, you can do that. And you can also figure these out if you only have one and then the angle, because we know about sines and cosines and doing the inverse of those. Oh, I wanted to bring that up too, right? You may all think that trigonometry is beyond us and you might not have your old scientific calculator like I do, right? However, a thing that you may or may not know is that if you get into those of you with iPhones, I don't know about the other kind, but if you get into your calculator, when you look at it, first of all, there's your calculator, right? Do that. And you will see down at the bottom that you've got sines and cosines and tangents. So you can figure things out if you know SOHCAHTOA. And then if you press the second button, you'll get the inverse of them. So if you know the tangent is this number divided by that number, and you want to know the angle, you do the second tangent of those two numbers, or the inverse tangent of those two numbers, it'll give you the angle. And then you can go into your chart and figure out what your candle power value is at that angle, and then you can do your calculation. Okay, so the trig all works together to get you into the candle power charts to get you the right I number. Okay, and you can figure out the D number and the other angles based on your geometry of your space, your fixture to the point you want to look at. Super important to understand the relationship between all that stuff. Does anybody have any questions?
I do not.
Okay. Don't, yeah, again,
But
one
I'll
of
take it, but if not,
okay, yeah, they did a weird thing. In any case, all right, here we go. So they have a couple examples working here. Again, I can't see through me to see the exact numbers there, but it's the whole concept, right? And you guys don't have to do it. I'm not going to make you. You figure out your intensity, you divide it by the distance squared. This is the easiest one of all. Whatever that value in orange is, divided by 7 squared is your foot candle value, right? Because you have no cosine things to be dealing with. You go to this one, and you'd have to go into the candle power table of that particular fixture, figure out what's happening at 30 degrees from straight down. I think they put that in the orange number over there to the right. So now we would have from the candle power chart, the intensity of orange number, they've already told you you have 8 feet to go. So there's your D for the D squared part of the equation. So you have I and you have D squared. Now you need to do the cosine of the angle. And what would be the incident angle of this particular number over here, everybody? Opposite interior angles.
Incident angle would be 30 degrees for this one, right?
Yep, bitchin', right? It exactly would be 30 degrees. So incident angle is, perpendicular to your point and then over to where the light's coming in. So because of opposite interior, oh, what I just did. Opposite interior angles, right? If they gave you up above 30 degrees is the way you're going to analyze, you know that it's a 30-degree incident angle as well. So the cosine of 30 degrees, back from SOHCAHTOA, you could even look it up, but it is what it is. You throw that into the calculation and voila, you have how many foot candles should show up if you were to hold the meter that I lost at that point. And in this one, what they did is they tipped that fixture so that now you would be using the nadir candle power in orange, along with that same geometry setup, right? So instead of using 30 degrees up from straight out of this fixture, now we're using the straight out of this fixture number because they aimed it. So if you're thinking about track light calculations or something like that, that's what this would be valid for. Okay. Here's where they try to do math jujitsu again, I think, with the sign. But remember, no matter what angle they give you, right, you could go the parallel, go the other side. So we know that on the other side of this particular thing coming in, there'd be 30 degrees from the wall out to the line coming in. But we don't want that one. We want it not from the ceiling out to the line coming in, but from the wall straight out coming back to it. And we know that since that's 90 degrees, take 30 away from the opposite angle, you got a 60-degree incident angle, and that would be your cosine number, which you could use the straight out candle power of the way that they tip that fixture in your formula. Okay, so again, opposite interior angles are equal. All the angles add up to 90 degrees coming off of that normal to the wall. We always want to think about the incident angle and then be able to use trig or whatever it is we need to get the distance squared to plug into that equation. Right, and these are just, again and again and again. This time again, they're using the straight. They kind of do you a disservice in always using these straight out values as opposed to showing you what like a 2x2 would look like and how you'd have to dive into a chart to get these values because they just kind of feed them to you here. But again, you got to remember, you're going to be diving into these charts to figure out what number to use for your calculation. Right here, this is actually super cool. Lots of things like track lights, right, will give you charts like this. And what they've done here is they've done all the math for you, right? They went into E equals I cosine theta over D squared, and they figured out where it says FC, what the incident foot candle number would be with whichever of these things that you were using over here on the left-hand side, your spot, your very narrow flood, or your narrow flood, right? Straight down, they did I divided by D squared, and they got FCs. Right. And you can probably go through the math between where they show you on the left-hand side that 15,960 candela. If you divide it by 25, you should get 638. Let's see if that worked. 15,960 divided by 25. And voila, 638.4. So they did all the math for you. Now, here's the cool part. They go to L and W on the side here, and that's where that 50-degree beam number hits the edge of, quote, the circle. It's not necessarily a circle of light that ends at that spot, right? That's where 50% of the max candle power makes the edge of where the beam hits the ground. There's still light outside of that, right? We're still falling off from 50% out to 10 or, 0, right? But this gives you an idea of where, up to the 50% value is concentrated. And that's super handy to kind of know if you're going to be able to say, cover the piece of artwork on the wall that you want to cover. If it's an 8-foot piece of artwork and you look into the chart here for a 30-degree aiming angle where you can put your fixture and you get 3 feet by 1 foot, you have to have like 10 of these to do your 30-foot, whatever it is, without doing calcs. Maybe you get away with 8 when you come back and do it, but it'd give you at least a little bit of an idea of how much the main beam is going to cover.
They Do they make these for gimbal?
You know, they probably should, but they don't typically. It's usually, like I said, for okay, if we redefine gimbal, they will do these kinds of things on cut sheets for adjustable architectural fixtures with beams out of them. When you get to sometimes a thing called a gimbal, it can be very fuzzy, and there's just not a lot of difference when you aim it one way or t'other, so they don't bother. Does that make sense?
I think so.
So architectural recessed fixtures that have very nice beams, and you can choose your beam spread, right? So you can get a 15-degree beam coming out of that fixture and tip it to the wall at 45 degrees to hit your whatever it is on your wall, or you get a 40-degree beam out of that fixture and do it. The beamed fixtures tend to have this kind of information to them. Lots of, quote, gimbals can be very fuzzy and inexpensive, and there's just not a lot of beam to it, so they don't bother.
All right.
Point method. This is what we just spent all of our time on. And 6:33. I do want to try. I'm going to try to get through the rest of this pretty quick, guys. All right. So lumen method. This was a way for performance information to be put onto a cut sheet, so you could just take information like your room, your fixture, throw a number of fixtures at it, and get yourself an average calculation without ever doing the point by point and adding them up and dividing them. Okay, that's what the lumen method does. And the lumen method is predicated on taking your IES file, running it through a utility, and developing what's called a coefficient of utilization. And that coefficient of utilization varies based on the characteristics of your room, and they make a wonderful chart to where you can use yet another formula, right? Where it counts the lumens out of your fixtures. You apply the coefficient of utilization, and you can end up figuring out what your average is going to be in the room. And there's a nice explanation of this stuff going through here. Okay. So again, illuminance, lumens per unit area. We're figuring out the sum total of lumens. We're dividing by area. We're getting an average. Okay. So phi means lumens. A means work line, right? Work plane, or the work plane. So lumens times your coefficient of utilization, which we develop based on the performance characteristics of the fixture, times your light loss factor. We could do light loss factors for a half hour, but we're not. Divided by your work plane area, and you have average foot candles. Just average. Doesn't talk about maxes, mins, or anything else. Now, CU, again, is based a lot on the characteristics of your room. I think we go to that next. Again, diffuse, uniformly spaced luminaires, one type in a room. All right. So here she is, the CU table. The things to take from this table, even though you're probably not going to be doing these by hand average calculations yourself, there's lots of cool utilities that do this for you. But if you take a look at this CU table for a particular fixture with a particular distribution, right? That's what's over on the right. This table, without having to go into details, right? It gives you that CU to put into that formula based on a 20% effective floor reflectance. I've got some other cool charts that if it's not 20% floor, what do you do? Right? I don't think I'm going to show that because again, time. All right. But you can modify this as well. So, but most people talk about a standard reflectance value for interior spaces is 80% on the ceiling, 50% on the walls, and 20% on the floor. So this is based on 20% floor effective cavity reflectance. So that's the floor up to wherever your work plane is. And there's a whole set of charts for figuring out what that number is to then figure out what the modification factor should be to this chart to then go into the chart. So details, you're not going to do it, right? 20% floor. Now, if you look at the top of this thing, you will see columns for ceiling reflectances that change in the space. And if you dip down into the chart, you'll notice that as you change your ceiling reflectance, for the same value of wall reflectance, you start to get slightly less of a cavity ratio. So, you're going to get slightly less foot candles when you run that CU through that formula, right? So, but not a terrible amount as you roll through this. So this is mostly a downlight. I'm sure that's what number 3 shows there that I can't see. All right. Then if you go down to any particular ceiling reflectance and you start to look at the walls for any particular room cavity ratio, that's what these numbers are on the left. If you go to any one of those and you start to go down the walls, you'll notice that in the lower room cavity ratios, as you change your wall reflectance, it changes, but not a heck of a lot. You go from at room cavity ratio 1, you go from 113 to 105 underneath this 80, so you lost 8% roughly. If you go farther down in the room cavity ratio chart, notice that changes a lot. So this is where we need to talk about what the hell room cavity ratio means. And somewhere, oh good. So room cavity ratio, the actual number is 5 times the length plus width divided by the length times the width of your space. And what it turns out is as that number grows, as room cavity ratio grows, your room becomes more and more and more like a grain silo, right? So room cavity ratio of 10, grain silo. Room cavity ratio of 1, big, flat, open space. And what that has to do then is how many of the lumens leaving those surfaces bounce off the other one and come back. So in a really tall, your room silo, if you try to do an indirect light and it hits this little patch of ceiling up here, how much of that light's going to make it down to the floor? Well, if we go back and we look at the difference between a room cavity ratio of 1 in any particular column and a room cavity ratio of 10 in any particular column, notice we lose almost half our light. So indirectly lighting the ceiling or actually any kind of lighting way up high in a skinny space, not as much of that light's going to make it down to the bottom. Now, that changes based on whether you have a spotlight or a floodlight, whether you have a diffuse surface or whether you're trying to indirectly light, say, a tall ceiling skinny space. That's not going to work very well. So those numbers will change, but you get the concept, right? Big open spaces with surfaces that interact with each other, a lot of the light's going to make it up and down. A lot of the light in a big open space from the ceiling is going to make it to the floor, and very little of it interacts with the walls. And that's why wall reflectance changes in short spaces don't change so much, but wall reflectance changes in tall spaces do, because the walls count more in that tall space if you're trying to bounce light down to somewhere. So warehouses, the walls don't matter. Small offices, they certainly do. As a practical thing, right? So yeah, I wanted you guys to get that sort of understanding. Then as you change reflectance values based on the type of fixture you have, you can, well, both reflectance and then your geometry, you'll get less or more light depending on those variables. Questions? Great. All right, so room cavity ratio, we talked about that. Cavity, cavity, cavity. There's these different cavities. Where's the fixture relative to the ceiling? There is no cavity if they're recessed. If there is a cavity, there's a way to take into account some of the light that's going to bounce up and down and out of these things, right? There's your room cavity ratio number calculation. So how heights and lengths and widths, interact with each other. Tall, skinny spaces result in high room cavity ratios and lower amounts of light making it down from all the way up there. It's intuitive if you start to think about it that way. Right? Oh, and here's what we just talked about. Ooh, reflectance values. Again, when walls become important, reflectance value of the wall becomes important. Stairwells. Ooh, stairwells. It's very important what your wall reflectance is on a stairwell, because there are very defined foot candle numbers that you have to have on stairs to meet safety requirements. If you paint the walls black, you're not going to do it. Paint the walls white, you got a better chance, because you're going to be able to bounce light around and get it down to places, right? And this is just some examples of different reflectance characteristics. One of the more common ones that you may or may not utilize, I try not to, is concrete. Brand new concrete's 40% reflective. So if you get into a garage, you could maybe use that for reflectance values. I try not to in garages anyway, because they're going to fill with cars. But that would be on the high end, right? If you wanted to bounce light around your garage. And then look at the woods, right? Everybody's, I want to indirectly light my wood ceiling. Well, you can. But if that's going to be your only source of light for the room, compared to, say, a ceiling tile that's 80%, you'll have to throw twice as much light at light wood to get the same amount of foot candles coming out of it. And then medium or dark, then you have to do 4 times the amount of light. So can run into energy problems if that's your only light source. So in cases where you have beautiful wood ceilings, it's kind of nice to light them so people can see them. But then you might have another source that's more efficient at getting light down for, something else. If there's anything else there that's really See, here we're back to coefficients of utilizations. Oh, here's that spotlight example versus something wider. Notice the spotlight in the silo on the right at room cavity ratio on the 9, you can get to 88 of it making it to the bottom, whereas the thing on the left, only 72 makes it into that calculation to get your foot candles, right? Difference between a spotlight in a silo versus something wider. So that was kind of handy. Right, we're not gonna, we already did all that. Remember I said we could do a half hour on light loss factor. We'll do 30 seconds, maybe a minute. Light source lumen depreciation used to be lamp lumen depreciation, but now we use LEDs, so they changed it, right? That is a long discussion in and of itself. You will be receiving on cut sheets things that tell you a certain depreciation number at a certain time in the future. L blank at however many hours, and that is a result. We talked about that last time. It's a result of the data gathering and extrapolation into how the chip depreciates and then at what temperature we're running at in our fixture. And so we're going to tell you that, you know, 60,000 hours down the road will be at 80% of output. So you can get a number from there at a time from a fixture, but you got to be consistent about maybe what you're trying to use for that number. It should vary for every fixture. A lot of people default to just a number, just to let you know. Luminaire dirt depreciation. An indirect fixture is going to get stuff on it that stick and depreciate your output more than a direct fixture. There are many charts and things that I could show you, but we're not going to do it. But know that it is something to maybe keep in mind. If you're in an industrial situation versus an office, you're going to want to have more dirt depreciation in your calcs to figure out what you're going to have over time. Same thing goes for room surface dirt depreciation. Lots of people leave out both of those. They roll to the lumen depreciation number, and with LEDs, it's pretty high, and away you go. And then, you know, year and a half down the road, there's less light than you wanted, and people want to understand why. And oh, that's it right there. All right, room cavity ratio calcs. You guys are not going to do that. We're not going to do the. We all know about illuminance. That's how many drops of light. Right, lumens reach an area divided by the square area. If you're doing it in metric, the area is square meters. If you're doing it in English, it's square feet. And the difference is the ratio of a square foot to a square meter. Right? Our room cavity ratios, understanding silos versus long flat things, and light loss factors. Now, I've talked to you about modeling before. Some of these models are really cool and people have spent a lot of time doing them, but that's the thing. You can't just build a room, apply some reflectances and render it. Is that really what it's going to look like? People spend a lot of time, energy, and effort with renderings and the information that goes into them to get things that might come out of them that may look like what it's really going to look like. But that's really hard. And part of the reason it's really hard is a printed render versus a render on a screen versus real life. Each one of those has a range of luminance values that's coming off of it that are very different from one another. So a printed rendering is never going to look like the real thing, although it could come close, depending on the luminance ranges as you look around your space. Here is simple. Okay, we talked about lumen method calcs where you had one kind of fixture to an average in a space. Here she is, right? This does those calculations for you. So instead of you doing the room cavity ratio yourself, it calculates that, it dives in, it pulls those numbers together for you, and voila, you get answers. Where in a 20, notice on the left-hand side, they've got inputs for this particular utility, where you put in a room definition, 20-20-20, height 10, work plane 2.5, room reflectances, and then you plug in 30 foot candles under criteria, and in the top right section over there, it tells you that with 16 fixtures, you get 29 foot candles. Notice it says it wants you to put them in a spacing of 5 by 5 feet. Well, this is where you have to start to use these tools and then use your own brain to figure out whether that's realistic or not. You're probably not going to take a 2 by 2 fixture into a room and put them on 5 by 5 centers. That's ridiculous, right? That's 25 square feet per fixture. That's probably way too tight. So whatever this fixture was and the lumens that this fixture had are probably not a great fit for you. And maybe you go find the next lumen rating up. And when it gets closer to a reasonable spacing, you'll be, okay, I get it. And if the reason, the spacing's 8.67 by 9.54 feet, you say, you know what, I can do 8 by 8 and move along. Right. So you can use these utilities to give you quick feedback to get you one kind of fixture to an average in a room spaced evenly. Okay. Then you do point by points and renderings. We talked a little bit about the rendering thing. Point by points, the numbers themselves, though, don't lie. They're there no matter what kind of interpretation is done, interacting with surfaces and all the rest of it. And there we have the example of numbers. You can use contours to show people things or not. Uniformity ratios indoors versus outdoors are very different. We could have long discussions about those things. Different ways that programs do it. Look at this thing on the right. Somebody did a very nice job over there on those curtain looking things of getting some kind of texture in there, right? And then they spent the time to do the ceiling grid with different reflectance. It would take a long time to put together even that render. Is it accurate in the end? We don't necessarily, right? I'm not going to go too much into those things. Lumen methods, point by points, field measurements. Lots of municipalities would love people to do an analysis of existing light fixtures and tell them the foot candles outside. Well, the problem is any existing light fixture that's been around for more than a month or two has depreciation characteristics that change the output of the fixture, the shape of the output of the fixture. Think dirt or yellowing lenses. You can't just apply a number to those because they change the distribution of the fixture. So the only way to really be accurate, if they're even interested in accuracy, right, in what an existing installation is doing, is to go out there and actually measure it, right? That can also be handy when you're contemplating changing a lot of your light fixtures out in a particular building. See what people have now versus what you might design to if it were a blank slate. If you go into a place and they have 20 foot candles now and you would have designed to 50, they'd probably be happy as clams with 30 or 35. So do they really need, the 50? So there's things like that. The field measurements can help you decide on how you're going to proceed with whatever it is that you're doing, right? And just ways to do that, different ways to quadrant areas and things like that to figure out averages. The more the merrier. Luminance meter, I talked about that on the left. They started several $1,000s. Color spectrometer, if you're into color, the middle guy. And then I have at the office a Minolta, very much like one of the ones over there. And I've got a little cheaper one that I brought home and lost to show you guys for just a regular illuminance meter where you hold it at the surface where you want to measure foot candles, press a button, lean back. Don't get in the way of it, right? Of lights. You don't want to shadow lights. You don't want to bounce light. If you take these things outside at night and wear white clothes, you're getting false readings unless you get far enough away, right? And that's another big difference on the meters. And then I'm going to see if my compatriot's ready to go. Meters for indoor lighting levels be very different from meters from outdoor lighting levels. Outdoors need to be much, much more specific and sensitive, because outdoors you're measuring things in units of individual foot candles, 0.1 foot candles, 0.0 something foot candles. Indoors, if you're off by a foot candle on 40, it doesn't matter much. Outdoors, if you're off by that same foot candle on 0.5, it's ridiculous. So be careful about the light meter you buy, depending on what it is you're going to be doing with that light meter and how sensitive it is at what levels. All right. I got 40 minutes for you, man. Are you there? Carl?
Yes, I am here.
Ah, all right, everybody. So that was lighting. Any last questions before we give Carl some time?
Nope. Thank you though. That was a lot, but that was great.
It is a lot.
Yeah,
Right?
it's
It's
a lot of
really,
info.
yeah, it's really hard. But when you finally start to get the relationship between things, it makes life so much easier with everything you have to do.
Yeah.
With that, I will stop sharing and I will actually leave. You guys have a fantastic rest of your night.
Thanks.
Thank you, Bob.
Thank you.
Ready, bye.
Excellent. Perfect timing. Cole, is that you with on the IES MC duties tonight?
Yes, yes, it is. How you doing, Carl?
Excellent. Well, wonderful. Thank you, sir. Cole, if you want to stop recording to close out Bob's module, and then we'll start recording again for
Sure.
rest of this one.